All right, hi everyone, and welcome to today's seminar. Today we're going to have two early career speakers with us, Dr. Saddie Elliot and Dr. Simone DiMatteo. Sadie will be giving our first seminar today. So Sadie grew up in South St. Paul, Minnesota. She received her Bachelor's of Science in Physics and Mathematics from Osberg University in 2016, working with Mark Engerbretson on emic wave occurrence patterns relative to the plasma pause. She then moved on to the University of Iowa, where she received her master's in physics as well as her PhD with a focus in astrophysics. Saddie's PhD thesis focused on plasma waves and particle interactions in Jupiter's polar regions using data from the Juno spacecraft. Following her PhD, she started working at the University of Minnesota with Dr. Cynthia Cattell's research group. Currently, Saddie's work focuses on studies of chorus and microbursts in the radiation belt and the radial evolution of intermediate frequency waves using the Juno and Cassini satellites. Today, I'm delighted to have Dr. Saddie Elliot here with us to discuss quantifying the size and duration of microburst-producing chorus region on the 5th of December, 2017. With that, Saddie, if you would like to take it away.
Okay, thank you. Let me share here. Okay, can you see my screen okay?
Yep.
Okay, perfect. Well, thank you for having me today. I kind of shortened, I guess, my title a little bit to make it a little broader, because I'll be kind of focused on chorus and microbursts and studying the connection between the two and the importance of that. So my overview, I'll introduce and give some background on chorus and microburst precipitation, and also talk about the motivation behind studying these things. And then I'll go over our December 5th, 2017 event study, which was the focus of a recent GRL paper, and talk about the different instrumentations and data sets that we used, as well as the observations and results and conclusions from that work. And then I'll briefly go over some current and future work. So the motivation behind studying microburst precipitation and its interaction with chorus waves, first off, the first thing that comes to mind is the dynamics of the radiation belts. So as many of you know, the radiation belts are highly dynamic, and there's a lot of moving parts to them. We have lots of competing processes that contribute to the dynamic formation as well as depletion of the outer radiation belt specifically. And we have competing energization, loss, and transport processes that are all occurring simultaneously, and they're also energy dependent. So this makes it very difficult to separate out and quantify the relative importance of each of these processes. And one example of that is we have a big question about depletions and loss and the direction of those depletion and losses, whether the electrons are being lost out of the magnetopause or if they're being lost into the atmosphere. And for one example, there's a significant loss process called magnetopause shadowing. And these have been incorporated into models, and we find that when that happens, they don't really well capture the observed loss, especially at high energies. And so we really need additional loss processes included in these models. And then secondly, I've included, once these electrons are lost into the atmosphere, they have a very large impact on Earth's atmospheric composition. And Josh Patet actually gave a really good talk in this series on energetic particle precipitation and the impact that it has on the atmosphere. And he talked about how, when these electrons are being lost into the atmosphere, they cause significant enhancements in the Hawks and the NOx, which in turn causes depletions in the atmospheric ozone. And this plot here is kind of showing you that the altitude of that the electrons deposit their energy depends highly on the energy of the electron as well as the density of the atmosphere. So we really want to understand the fluxes and the energies of these precipitating electrons in order to fully understand the impact that they have on the atmosphere. I also wanted to mention that there have been studies done specifically on microburst storms. There was a paper in 2018 by Sapala et al. And they found that, they had a really long duration storm, and this significantly altered the Hawks and NOx, which caused a quite substantial decrease in the ozone. And then the last kind of motivation that comes to mind is the connection to the aurora. So there have been recent studies, specifically a lot of studies but from Mike Shumko et al. And this is a plot courtesy of Mike, as well as this kind of image here showing you a correlation between Themis and Sampex observations. So we see that they're correlating microburst precipitation in relation to the pulsating aurora. And this is important because in the past, there have been questions on the connection between higher energy microbursts and lower energy microbursts and the connection between the two. So typically the aurora is generated by these lower energy electrons. However, there have been questions on whether or not the low and the high energy microbursts are generated by the same mechanism. So this is an important study that kind of shows that there's likely a connection between the two. And then in addition, I wanted to mention Jupiter because my background is on the Juno spacecraft. So this is an image from Juno showing you the aurora at Jupiter. So the aurora is this, process that's observed not just at Earth, but on other planets. So being able to study the generation mechanism at Earth can in turn help us understand these plasma processes in different plasma regimes. Okay. So I'll just briefly go over microbursts and chorus specifically. So microbursts are these impulsive injections of electrons, and they occur from about a few keV up to an MeV into the upper atmosphere, and they're typically very short duration, so less than a second. And they're commonly observed from about L shells of 4 to 6 in the morning time sector, although as I'll mention later, this size of this region and the location of this region is not very well constrained. And the reason why we study these microburst events, aside from the motivation that I just talked about, is that they may be a significant source of electron loss. So here I'm showing a figure on the left from this Laurentian et al. Paper. And this is basically just showing you that even though the microbursts, which are shown as these orange spikes kind of on top of this background precipitation, even though they're very short-lived, they can have fluxes an order of magnitude higher than the background precipitation, and therefore they may be a significant loss mechanism for outer radiation belt electrons. And this is a plot from a more recent study, which was done on the Firebird CubeSat from Brenneman et al. And I'll mention this paper later on as well, but just showing you those sub-second spikes in the data and how we pick out these microburst events. And in order to talk about microbursts, we have to talk about how they're generated. And they're typically thought to be generated via interaction with chorus waves, which are generated near the equator. And I wanted to also mention that these microbursts have been observed for many years. The lower energy microbursts have been observed since the 1960s. So then background on chorus waves. So chorus is a plasma wave that propagates in the Whistler mode, and they occur between two frequency bands, which are separated by the equatorial electron cyclotron frequency. You have an upper band and a lower band. And typically, the importance of each is the particle populations that they interact with. So lower band chorus is kind of the one that we're focused on because those are the ones that can generate these electron microburst events. And so yeah, they're important because they're thought for many years that there's strong evidence that they're the dominant scattering mechanism for generating microburst precipitation. And this is due to the similarities between the global distribution of chorus and microbursts, the fact that they both occur on the morning side outside of the plasma pause, and then also they have very similar sub-second structure. Okay, so these are some of the open questions regarding chorus and microburst precipitation. There's more than this list, but I've just listed a couple here. So the first being, we don't really know where the interaction is taking place between chorus and microbursts and the exact scattering mechanism that is happening. So, there's a question of whether the interaction happens near the equator or at more off-equatorial latitudes. And the Brenneman et al. Study in in 2017 was kind of the first study to look at a connection between chorus and microbursts along the same magnetic flux tube. And they did find that it likely indicates that the interaction happens at off-equatorial latitudes of about 20 to 30 degrees. But this is still kind of an open question. As you can see from this plot here, you have observations of chorus at these equatorial latitudes, and then low altitude observations of microbursts. And this region in the middle here is kind of labeled as this undersampled scattering region. So that's kind of an open question in the field. And then the second one here, I bolded because that was kind of the main focus of our recent study, and that was the magnetic local time and the L shell size and duration of these microburst producing regions of chorus. So this is important because we need a very well-constrained size of the region in order to determine whether or not microburst precipitation constitutes a significant source of electron loss. So if the region is rather small, it might take a really long time to deplete the outer radiation belt. Whereas if it's a large region, it will take less time and maybe be on the order of a substorm. So that's kind of a large open question in the field. And so how do we answer those questions? Well, the ideal situation would be we would be having plasma wave observations at high latitudes and then microbursts at low altitudes. Kind of the most ideal situation would be have measurements kind of along that same magnetic flux tube, making measurements of wave populations and their how they interact with and alter the particle populations. But kind of the best case scenario at the moment is that we'd have an equatorial satellite like Van Allen probes attached to the same magnetic field line as a low altitude satellite such as the Firebird CubeSats. So there's been collaboration between the RBSP team and the Firebird team, and they found that there have been a total of 265 close conjunction events where we have these simultaneous or these measurements along the same magnetic flux tube. And this occurs over about 81 days. And this is when we have high time resolution burst waveform data from Van Allen probes. And then we also have high time resolution electron flux data from Firebird in order to detect these microburst events. So this is just showing the statistics of this data set. The orange is showing you the events that have this high time resolution electron flux data in order to detect the microbursts. And this is just a linear versus a log scale to kind of highlight those orange bars. So the first kind of study that used this conjunction data set was the Brenneman et al. Study, which I mentioned earlier. And so this is a figure taken from their study. And this was a conjunction event, kind of the best conjunction event so far. And you can see the similar substructure between the chorus wave amplitudes on the top here, and then the microburst flux in the middle here. And again, one of the main results from this study was that they found that the interaction happened at off-equatorial latitudes. And they also estimated the lost timescales for microburst precipitation. And they found that microbursts may be a significant source of electron loss. And then another study that I wanted to mention, which has basically looked at the size and duration of a microburst region, was the Anderson et al. Study. And they included microburst observations from Beryl, AC6, and Firebird. They did not include any chorus observations in this study, however. And they did find that the size and duration of the region was rather large, 4 hours in magnetic local time and 5 in L shell. And so this kind of just highlights that the size of this region could be rather large. So for our particular study, we tried to use the best case scenario that we could have. So we included all measurements that we had at the time. So we had chorus measurements from Van Allen probe, A and B, and then we also had ARASA observations, and then included ground-based VLF data of the chorus waves. And this is on the right-hand side, we're showing chorus wave observations from Van Allen probe B. And then we included the microburst measurements from both Firebird CubeSats as well as the Aero Cube 6 CubeSat, and then we supplemented these with particle flux measurements from the POSE instruments. Now, POSE cannot resolve microbursts because it has only a 2-second cadence. However, we utilize the data in such a way, as described in the Patet et al. Paper, where we tried to isolate times when the bounce loss cone flux was due to interaction with chorus waves. And if you want to know more of the details on how we process that data, you can look at our GRL paper as well as Josh's paper here. But the reason why we supplemented this was because Firebird and AC6 give you pretty good, MLT. They do a good job in, L shell. They do a good job in measuring various L shells. However, over a time range, they don't do a very good job in magnetic local time. And so POSE has pretty good coverage in magnetic local time. So we're trying to supplement that with those observations. Okay, so here are the results from this study, and I'm going to kind of go over this rather quickly because there's a lot of details here, but if you're interested, you can read the paper. And these plots are rather complicated as well, but I'll show kind of our resulting plots is kind of the main takeaway. So here, for this event, we had pretty close or pretty continuous chorus for about 30 hours or so. And then we wanted to look at this data and separate it out into 9-hour time periods. And this was partially selected because of the orbit of Van Allen probes, the times when the spacecraft is outside of the plasmasphere, as well as ERASA, but also to provide sufficient spatial coverage of the inner magnetosphere. And so on these plots, we have plotted the chorus magnetic spectral density, the mean spectral density of the chorus waves, shown as the rainbow color bar plotted on top of the locations of the spacecraft of Van Allen probe and ERASA. We also have ground-based VLF observations of chorus shown as the magenta lines. And then in the background, in the grayscale, we've shown the POSE observations of regions where they've detected high fluxes of bounce loss cone flux, indicating that that's likely a region where there's microburst precipitation happening. And then we've also included the actual microburst observations from Firebird and AC6 in these red stars. So here I kind of listed the important chorus observations, and then in the next slide, I've listed the microbursts. I'll just mention a few important points. One being that for all of these time periods, the chorus kind of initiates around 6 to 7 magnetic local time. However, you can see that there's really no coverage of the spacecraft prior to that. And so likely we are underestimating the size of the region. So ideally we'd have a bunch of spacecraft measuring the chorus throughout this time period over a wide range of magnetic local time, but that's not the case here. And then this is just kind of pointing out some of the microburst and precipitation observations. You can see that there's some large regions of precipitation observed by POSE, and sometimes they overlap with the microburst observations from AC6 and Firebird. One thing that I wanted to note was, at least for this second time period from 12 to 21 o'clock, you do have this rather large precipitation region kind of past 14 magnetic local time. And ERASA is in these regions at that time. However, they don't measure any chorus waves during this time, but they did show indication that they are measuring emic waves. So it may be that this precipitation is due to some other type of wave particle interaction, like interaction with EMIC waves. And then this is another way that we can plot the data. I know there's a lot of information here, but go ahead and look up our paper if you're more interested in this. But basically, the two top plots are plotting the same data on the previous slides, but just for the full 30 hours. So we have magnetic local time versus time on the left, and then L shell versus time on the right. So again, we're plotting the mean spectral density of the chorus waves as the rainbow color bar. And then POSE is now plotted, instead of plotting it as a grayscale, we plot it as this kind of orange to purple color scale. And the reason why that is because we've blacked out certain regions. And so you can see these kind of blacked out regions, and those indicate the regions that we really can't say much about the data because we don't have any chorus wave coverage. So there are no spacecraft coverage during that time. So you can see that there's large gaps that we have here due to limited spatial coverage. And then the bottom two plots are showing you the same things, except for this time, instead of the rainbow color bar being the chorus magnetic spectral densities, it's the electron fluxes measured by MAGICE and HEP. And this is just to kind of indicate that we see, strong electron precipitation where there's increased microburst flux corresponding with regions of high electron fluxes from MAGICE and HEP. So this is kind of the main takeaway plot of this study. We really wanted to constrain the size and duration of these regions. So what we've done here is we've made plots of the microburst and precipitation extent as these green color bars. And then we have the chorus extent as these dark blue. And you can see that that's a subset of the chorus coverage because we're pretty limited by the chorus coverage. POSE has pretty good spatial coverage overall, but we're more limited on the Van Allen probe and ARASA coverage. So you can see that there's, overlap between the microburst observations and the chorus observations. So those regions we use as our lower bounds for the estimates on the size of the region. And then we include regions where we have microburst precipitation observed, but there's no chorus observed due to lack of coverage as our upper bound for the size of the region. And those results are shown on the right sides here for each of the 9-hour time periods. So based on this, we can estimate, upper and lower bounds on the size of the region, and we find it to be ranging from about 4 to 8 delta MLT and 2 to 5 delta L, so rather large regions. And I've also noted here that all 3 time periods had limited chorus coverage prior to 6 MLT and also beyond 6 L, so we're likely underestimating the size of the chorus. So this is kind of the main takeaway from our event study. We really wanted to constrain the size of this region, and that's important because it's important to understand whether or not microburst precipitation is a significant loss source. And I didn't mention this, but I have it listed here. We did also look at the chorus wave normal angles, and we found them to be consistent with other studies, such as the Colpitts et al. Study, which looked at observations of chorus waves on Van Allen probe in conjunction with ARASA propagating to higher latitudes. And they found that the wave normal angles varied from more quasi-parallel to more oblique at higher magnetic latitudes. And we found that to be consistent. And then we estimated the size of the region and found it to be rather large. And using these size estimates, you can estimate what the loss time scales would be. So we used similar approximations to what Brenneman et al. Used. And we found the loss time scales to range from about 8 to 12 hours. So therefore, we find that microburst precipitation is likely a major loss source of outer radiation belt electrons. However, this was kind of our best case scenario at the moment. We had all these available observations of chorus and microbursts. However, there are a lot of assumptions that we need to make, including the continuity of chorus observations between one observational point and another, as well as there are many undersampled regions of the magnetosphere. So this study kind of really highlights the critical need for constellation missions in the future. And then I just wanted to mention, this is some current and future work. We're working to utilize the full conjunction data set between RBSP and Firebird, and also include all other observations that we can use, similar to this event study. And we want to kind of bin the data, look at those upper and lower bounds, and also see whether or not the size constraints depend on geomagnetic activity. So that's all I have today. Thank you.
All right, thank you, Sadie, for a wonderful talk. That was really great. So I have a quick question. Given that we just put a number of papers into the decadal survey, and that you mentioned that this was a really lucky set of observations, what would you like to see in the future in order to really address and close this topic?
Yeah, so I mentioned the constellation missions. That would be like one of the main ones. I think ideally we would have, measurements of wave measurements as well as particle measurements kind of along a magnetic flux tube at varying magnetic local times. Now that can be kind of tricky because, when we're making in situ wave measurements near the regions where they're generated at the equator, measuring the the particles that are in the loss cone is rather difficult. So that's typically why we use those low Earth orbiting spacecraft. So, it's kind of a trade-off there, but that would be one thing that I'd like to see hopefully in the future. Yeah, maybe it'll make it in the decadal survey.
Hopefully. All right, excellent. Thanks again. If we get more questions, we can come back to them after Simone's talk. So our next speaker today is Dr. Simone DiMatteo. So Simone obtained his PhD at the University of L'Aquila in Italy in 2019, working on improving spectral analysis methods for the identification of periodicities in geophysical time series. He then moved to the US as a postdoc through the Catholic University of America and NASA Goddard Space Flight Center, where he investigated periodicities in the solar wind. Currently, Simone is the PI of a NASA ROSES project focusing on the geo-effectiveness of solar wind periodic density structures. So today, Simone will be discussing his current work, and in particular, Earth's magnetosphere interaction with the solar wind, with solar wind periodic density structures, and ULF waves and the radiation and the response of the radiation belt. So Simone, if you would like to take it away.
Thank you very much, Kyle, for the introduction. Make sure, can you hear me?
Yes, we can.
Okay. So thank you again. First of all, I would like to thank my collaborator listed below that helped for the work that I'm going to show today. And first of all, I'm going to introduce what are the periodic density structures, what are their effect on the magnetosphere, and particularly focusing on the ULF waves and the radiation belt response. So we define the periodic density structure as a solar wind density fluctuation that goes from a few minutes to a few hours. And in the figures on the left here, I show an example where the vertical line delimits 5 structures with a typical periodicity of 90 minutes. These are usually observed in solar wind stream with an almost constant velocity, as you can see. Sorry, as you can see here, I'm gonna put a pointer. As you can see here, this vertical line, as you can see, the boundaries of these structures often correspond to discontinuity in the interplanetary magnetic field, as you can see in panel D and E, and they are often in pressure balance, as you can see in panel F. These structures occur at preferential length scales in the solar wind. They are stronger in stream interaction region. And when elemental ionic composition are available, we often observe a similar fluctuation in those observations as well, suggesting that they can be of solar origin. The fact that this structure might come from processes that happen on the sun is also supported by remote sensing observation, as you can see in this movie on the left. Here are white light observation from imager and coronagraph, and here the brightness is proportional to the electron density, and the arrow here point to a region where there is a periodic expulsion of some structures that has also a typical periodicity of 90 minutes. There is also evidence of these structures closer to the sun, and this is a work done with the Helios probe, where these were observations at the 04 AU, where we, again, here in the top row, and the figure on the right, we see this fluctuation with a periodicity of 90 minutes. Also, this structure can also be a product of a process en route to the turbulence, or they might be modified during their process, during their travel to 1AU. So from the point of view of the magnetosphere, why they are important? So if we consider their typical frequencies as observed by in situ, obtained by in situ measurement that goes from 0.2 to 4 milliards, and we convert them in length scales based on the solar wind velocity, here I show 2 particular frequencies, we can see that they are of the same order of greater than the Earth's dayside magnetosphere. So they can engulf entirely the magnetosphere, compressing it, giving rise to a process that we are already familiar about, that is what we can refer to as breathing mode. And this figure is from Kekpo and Spes in 2003, And here the black line corresponds to the density as observed by wind. And the gray line is the busy component of GOES that shows similar fluctuation. So why this is important? Because if we notice that the frequency of these structures, they overlap with the frequencies range that correspond to the ULF wave PC5 waves that are particularly important for the dynamic of the radiation belt. From the point of view of the drivers of PC5 ULF waves, we have many mechanisms. They can be a result of the impact of shocks or pressure pulses, Kelvin-Helmholtz instabilities at the flank of the magnetosphere, and all of these can launch magnetosonic waves that then they can couple with field resonance of cavity modes. We also have process at the Bose shock. In particular, we can have force shock transient, in this case associated with the discontinuity in the interplanetary magnetic field that can modify the Bose shock or the magnetosphere launching this wave. We have also in the same frequency range surface wave, for example, at the magnetopause, the plasma pose that can cause this PC5 wave, as well as the internal process by injection of particle. So this is just to highlight how many mechanisms can occur in this frequency range. And I go back again to the same time interval that I showed in the first slide. On the left, there is again the density that I showed before. On the right, instead, these are the observations from the GOES geostationary satellite. The observations are in black. And from the top, we have the compressive poloidal and toroidal component. So you can see here the observation compared with the estimate of the Tsiganenko model using the wind data as an input, using only the magnetopause current in red and all the current system in blue. And you can see that even using this simple model, we are able to reproduce very well the observation on the compressive component, not only at the 90 minutes time scales, but also at this smaller fluctuation. On the other end, on the poloidal and toroidal component, while we can follow the general profile, we see these additional fluctuations that are more related to the PC5 waves. So this event highlights how this briefing mode mechanism at PC5 wave can occur simultaneously and at the same time. So it's imperative to understand better the driving waves or driving fluctuation. We need to be able to distinguish between all these different kind of waves at discrete frequencies. So in order to do that, we have developed a spectral analysis procedure based on the multi-taper method. The advantage of using this technique with respect to others is that we have two independent tests or two independent ways in which we can identify periodicity in the time series. One is the classic analysis of the power spectral density. In this case, using the statistical properties of the multi-taper method, we can have a robust estimate of the continuous background, that is this red thick line. And we can define the confidence threshold, in this case at the 90%, and all the portion above this threshold are candidates for indicating periodicity in this time series. The multi-taper provides an independent test that is called the F test, that instead is particularly sensitive to monochromatic and persistent fluctuation in the time series. When we combine them, we are able to pinpoint, to confirm that some of these enhancements are actual periodicity, and also to pinpoint better their frequencies. This is the time series that you see above is the same solar wind density that I showed for the event before. So we have here the 90 minutes periodicity that we also identify visually, but we also have another fluctuation at 2.6 milliards. So to better pinpoint this aggregate frequency component, we can also apply the same technique in form of a dynamic spectrum. In this case, again, on the solar wind density that is shown in the top panel. In the second row, instead, we have the dynamic spectrum. In the third row, we have the estimated background. And in the bottom panel, we have the ratio. And this dark area corresponds to a portion above our confidence threshold, where the red dots and the green dots represent the portion in which the two independent tests are satisfied. And here we can pinpoint better that the 2.6 milliards was actually occurring during this second structure. We can apply the same technique also to ground observatory to actually know better what was the magnetosphere response. And for this event, there were 181 ground stations available, and we organized them in 3 groups based on latitude, low, mid, and high. And in this plot on the left, the color scales are proportional to the percentage of ground station that actually identify the specific waves at specific frequencies and at specific time. To have a better view of their distribution, we also built these global maps that you see on the right. For each frequency range that is identified in the top panel, we integrate the power spectral density at each station in this frequency band, and then we interpolate it globally to have this qualitative map. And this was done for both the north-south on this left panel and the east-west component on the right. The time interval in analysis is identified by this green shaded area in the top left panel, where I show the CMH index as compared with the dynamic pressure of the solar wind in red and the A index below. So this was the response after the second interplanetary shock. And as we move forward, we can see the evolution, and we go toward the first periodic structures that was also characterized by a strong discontinuity in the magnetic field. And we can see here the PC5 waves that are localized, mostly at high latitude, but they can also show some dome-dusk asymmetry, as you can see in the panel in the bottom left. Now we go toward the structure in which there was the 2.6 milliards fluctuation in the solar wind, and we can see a drastic difference in what was the magnetospheric response, because all the ground stations, regardless of their location, both in the north-south and east-west component, were observing this frequency, highlighting that this was actually the breathing mode, in which also on the figure on the left, you can see that we reach almost 100% of a ground station observing this frequency. As we move toward the last part of the time interval, we see the A index is increasing, and here we have substorm activity occurring. And in general, you can see the enhancement of power, especially at auroral oval latitude that is identified by these dashed lines. And again, we have these more localized PC5 waves. And these also show how we can use this global representation to actually distinguish between directly driven waves or breathing mode waves between the more classic PC5 wave. As we mentioned before, these are important also for the dynamic of the radiation belt. In particular, they have an effect on the drift motion of electrons of the outer radiation belt that are at energy in between tens of keV of few MeVs. And for this event, focus on the 2.6 milliards, we actually were able to observe such response. And so in this figure, I show again this and actually zoom in on the interval where the solar wind density was observing this fluctuation. You can see in the second row the intensity of the magnetic field at GOES, and the vertical, following the vertical line, you can see the correspondence between the peak in the interplanetary space and the magnetosphere. And in the bottom row instead, we have the residual flux of electrons from one LANAN satellite, also at the geostationary orbit. And you can see how there is a nice correspondence between this fluctuation, and in particular at the end of the time interval between adjacent energy channel, we see some phase difference that is indicative of some drift resonance process. Due to the nature of these fluctuations that are compressive, they might also have a role in particle precipitation, and in particularly impacting due to pitch angle scattering of electrons into the lost cone. And this can happen in a direct way, in which the inward radial transport of electrons due to this compressional wave can move them in a region where they are inside the lost cone. And this is as can be seen in the schematic on the right, where the color line represents how the pitch angle of electron change due to inward radial motion. And the black area represents the loss cone, and you can see how this area intersecate. Or this compressional fluctuation can have an indirect effect, modulating higher wave modes, for example, Whistler mode or Emic waves. And on the figure on the right, I show an example from Brenneman 2020, in which this red dotted line is the dynamic pressure of the solar wind. In the top panel, we have the intensity of the magnetic field at Themis. And you can see in the panel D, the corresponding similar fluctuation in the influx of electrons at energy above 30 keV, and also in the power of these waves in the panel E. The precipitation was also confirmed by balloon in the bottom panel here, and these are X-ray measurement from the Barrel mission. This is a series of balloons that were launched in Antarctica, and the measured precipitation in form of X-rays produced by bremsstrahlung when the precipitating electron collide with the neutrals. So following the Brenneman 2020 work, we focused on the first and the second campaign of Barrel, in particular using the fast spectrum and the slow spectrum measurement. And we used them to find similar events where we could find this correspondence in terms of periodicity. And we compared the solar wind observation from wind. And since during the campaign, the cadence was about 96 seconds, what we first did was to reduce the fast spectrum and the slow spectrum to time series of counts per second with the same cadence of 96 seconds. And then we apply our spectral analysis procedure to interval of 3 hours to find similar event. So what we found are events like this one. So here in the top panel is the solar wind density. In the second panel, there is the intensity of the magnetic field that goes 13 and 15. And following the vertical line, again, you can see the correspondence between this fluctuation. And in the third panel, here is the time series that we built from Barrel, where the last 4 panels are the details of the slow spectrum, and on top there are plotted the same time series that we integrated. And you can see that there is a very nice one-to-one correspondence between the increase of the intensity of the magnetic field and the increase of the count-rated X-rays as sum of this Barrel. So we found 12 events similar to this one. And what we were able to conclude is that even though the events number is low for now, but we found that they were mostly localized in the day side, confirming also some results from Brenneman in 2020, and that they were mostly localized between 4 and 6 in L value, even though there is some evidence of 3.5 and 7.5 L for some of these events. What was interesting, though, was also that these events clustered in terms of frequency in 3 particular bands. That was between 0.6 and 1 milliards, 1.3, 1.8, and 2.3, 2.5. So to conclude, just some takeaways. Periodic density structures are often present in the ambient solar wind, and they occur at frequency that overlap with the PC5 ULF waves. And they are particularly important for the dynamic of the radiation belt and the loss of energetic electrons. And since they occur more often than strong drivers of magnetospheric activity, they can play a particular role in the preconditioning of the magnetosphere. So, thank you.
All right, thanks, Simone, for a wonderful talk. This is a topic that I quite enjoy, ULF waves and precipitation. Out of curiosity, have you looked at any of the rheometer observations which might that are available in Canada that might help to increase your stats for comparing precipitation with your discrete or periodic density structures?
So right at the moment, I've been focusing on the Barrel dataset. I'm still working on it to increase the statistic, and based on that, that was our first target. So right now, I have not looked at other observation from other instruments.
Oh, okay. Excellent. So that's all of our questions today. If anyone has any further questions, I would direct them to Simone's recent paper, as well as Sadie's recent GRL, which should be able to go into more detail of what was presented today. Our next talk will be by John Pedusik. He will be talking about interfacing Python with other coding languages, in particular C++ and Fortran. It'll be our next talk in a series of talks focusing on Python. So thank you again, Simone and Sadie, for wonderful talks. I hope everyone has a good week, and I hope to see everyone next week.
Bye.